Hi and welcome to the Sleepy Scientist. Tonight, we're going to gently float into the quiet, endless space between the stars. Not the kind of space where you lose socks or drop your keys, but the huge, silent space that stretches from one galaxy to another. This space might bend, loop, or stretch in ways our brains can't easily understand, just right for bedtime thinking. I should tell you now, this video might actually be a bit too interesting. If it keeps you up, I'm sorry. But if you find yourself wide awake at 3 a.m. thinking about the shape of a donut-shaped universe, at least you'll have something deep to talk about over breakfast. Before we cozy up into the curves of space and time, it would mean a lot if you gave this video a soft like or hit subscribe if you haven't yet. It helps this quiet little space on the internet grow. And if you want to, tell me in the comments where you're watching from and what time it is there. Maybe you're already lying down, maybe brushing your teeth, or winding down with a cat on your chest and a warm cup of tea in your hand. Wherever you are and whatever you're doing, I'm so glad you're here. Now take a slow breath, get comfortable, and let's begin our journey into the shapes of the universe, from flat and open, to closed, and even the ones that might fold back onto themselves. One quick note, this video is just for relaxing and learning. It's not meant as medical help or a cure for sleep problems. If you often have trouble sleeping, please talk to a doctor or sleep expert. Alright then, let's begin. What even is shape? It seems like an easy question. We grow up seeing shapes everywhere, triangles on road signs, circles on clocks, squares on screens. Kids learn about shapes before they learn to tie their shoes. We look at things and say, that's round, or that's pointy, or that kind of looks like a potato, and we all agree. But when we leave behind the world of plates and traffic cones and look out into the universe, things get really strange. Out there, past the clouds, past the stars, past even the farthest galaxies, there are no corners to count or lines to measure. Space isn't made of something you can hold. It isn't sitting on top of anything else, and still, it has shape. When scientists ask what shape the universe is, they don't mean what it looks like, but how it acts. In math, shape isn't just what we see, it's how things relate, how surfaces bend, how lines stretch out forever. Shapes can be sharp or smooth, seen or imagined. When we talk about the shape of space, we're not talking about design. We're talking about how everything is built. To get that, we have to go way back in time. Thousands of years ago, humans stared at the sky and wondered about their place in it. Even without telescopes or equations, people were already fascinated by shapes. They carved circles into rocks, lined up buildings with the sun, and noticed that the moon always showed the same side to Earth. These weren't just cool facts, they helped people survive. Seasons, tides, planting, they all followed patterns, and patterns are shapes. Geometry, which means measuring the earth, didn't start in labs. It began in fields and farms. Ancient Egyptians used it to mark land after floods. The Babylonians drew stars in grids. The Greeks took it further. A man named Euclid, often called the father of geometry, lived more than 2,000 years ago and built a whole system from a few simple rules. He believed a straight line is the shortest path between 2 points and that parallel lines never cross. For hundreds of years, Euclid's ideas worked perfectly. They helped explain pyramids and planet paths with clear and neat rules. But over time, people started asking new questions. What if parallel lines did meet? What if space didn't follow the rules we thought, especially when it came to huge, faraway parts of the universe? In the 1800s, smart thinkers like Gauss, Lobachevsky, and Riemann began to imagine space bending and curving. They dreamed up new kinds of geometry, where triangle angles didn't always add up to 180 degrees and where you could walk in a straight line and end up back where you started. These ideas weren't just wild guesses, they became the base of something called non-Euclidean geometry. Suddenly, shape didn't have to be flat or familiar anymore. Then came Einstein. When Albert Einstein shared his theory of general relativity in the early 1900s, he completely changed the idea of shape. Before, shape seemed like something still and unchanging. But Einstein showed it could move and react. His theory said mass and energy don't just sit in space, they actually bend it. Gravity isn't really a force pulling things together. It's what happens when space curves around heavy objects. Planets don't go around the sun because they're being pulled by a string, they move that way because the sun's mass makes space curve, and the planets are just following that path. Suddenly, shape wasn't just a math idea, it became something physical, something real. The universe wasn't like a solid stage anymore, it was more like a soft, stretchy sheet. Stars, black holes, galaxies, they all press into this sheet, making dips and curves that affect how things move. Even light bends along those curves. In fact, we've seen light from faraway galaxies stretched and warped because it travels through bent space before reaching our telescopes. This effect is called gravitational lensing, and it proves that the shape of space isn't just theory, it's something we can actually see. But here's where things get even stranger. We're not just talking about the shape of stuff in the universe. We're talking about the shape of the entire universe itself. That's like standing on a stage and trying to describe its shape without ever seeing all of it. Can the universe be flat and endless? Could it be curved and still have no edge? Could it loop back on itself like a giant cosmic track? To figure that out, scientists had to go beyond regular thinking. They needed ways to study shape from inside the universe since there's no outside to step into and look back. All our tools, all our measurements, are made from within. But by studying how light moves, how galaxies shift, and how ancient radiation from the early universe spreads out, we can slowly build a picture of the universe's hidden shape. Physicists use words like curvature and topology to describe this. Curvature tells us how space bends, whether it's flat like a sheet, round like a ball, or shaped like a saddle. Topology talks about how space connects. You could have space that's flat but loops back on itself, like how a video game map wraps around. Or you might have curved space that keeps going forever. These two things, curvature and topology, aren't always the same, but they both help us understand the universe in different ways. And here's one of the most amazing ideas in all of science. You might live your whole life inside a shape you can't even see. Space could loop, twist, or curl in a way that's completely hidden. You could walk, fly, or build telescopes, and everything might seem flat. But on a huge scale, so huge we can't even see it, space might be curved. It's like being a bug crawling on a balloon. If the bug is small enough, the balloon's surface feels flat. The bug could draw straight lines or build little bug houses and never know it's walking in a giant circle. Only by carefully measuring long paths or studying how light moves across massive distances would the bug start to suspect the truth. That's how space works too. What looks flat to us might really be curved. And that's what makes the idea of shape so fascinating. It's not just about what things look like, it's about how space acts. When we ask about the shape of the universe, we're really asking what kind of world we're moving through. Is it flat or curved? Does it go on forever, or does it wrap around itself? Is it smooth or full of strange bumps and twists? The shape of space affects everything, from how comets fly to how galaxies form. We may never see the whole universe from the outside, but each new discovery, each new math formula, and each starry night helps us get a little closer to understanding what kind of space we live in. So next time you think about shapes, don't just think about circles and squares. Think about the invisible outlines of everything, the quiet shape of reality itself. Now let's pause for a moment and think about something even weirder, the shape of absolutely nothing. Not nothing like an empty box or a clean desk, but the real kind of nothing. Total emptiness. A vacuum. No stars, no planets, not even atoms. just empty space stretching out in all directions. It may sound strange to say that nothing can have a shape. After all, shapes seem like something only things can have. Rocks, teapots, pineapples. But in physics, even the space between things, the emptiness itself, has a shape. In fact, it has two. Let's start with something simple. Imagine a flat sheet of paper. That's a good example of how ancient thinkers imagined space, flat, endless, and easy to understand. If you draw a triangle on that sheet, the angles always add up to 180 degrees. If you draw two lines that never touch, they'll stay apart forever. This is called Euclidean geometry, named after Euclid, a Greek thinker who lived long ago and helped create many of the rules we still use to understand shapes. Etri as a formal system. He laid down 5 postulates, simple rules that defined how lines and shapes behave. For over 2,000 years, those rules described the only kind of space anyone could imagine. But there was one postulate that always made mathematicians a little uneasy. The fifth one, often called the parallel postulate, says that if you draw a line and pick a point off that line, you can draw exactly one line through that point that never meets the first line. That sounds simple, but it's actually quite delicate. It works beautifully on flat paper. But what if the surface you're drawing on isn't flat? Suppose you're on the surface of a sphere, say a globe. If you try to draw straight lines, known in math as God d6, you'll find that things get weird. Lines that start off parallel eventually meet. For example, lines of longitude on Earth are all technically parallel at the equator, but they converge at the poles. On a curved surface, the rules change. The angles of a triangle can add up to more than 180 degrees. Suddenly, Euclid's system doesn't apply. In the 19th century, mathematicians like Nikolai Lobachevsky, Janos Boli, and Gottfried Gauss began to explore these non-Euclidean worlds. They developed entire systems of geometry based on curved surfaces. Positive curvature like the sphere and negative curvature like a saddle. These new geometries weren't just bizarre thought experiments. They were self-consistent, logical, and just as mathematically valid as Euclid's. It was a shocking discovery at the time. There isn't just one kind of geometry. There are many. This opened the door to a radical idea. If geometry could be curved, maybe space itself could be curved, too. Maybe the nothingness between objects wasn't flat and featureless, but flexible and dynamic. It just needed someone to connect the dots. Enter Albert Einstein. In the early 20th century, Einstein developed general relativity, a theory that redefined gravity not as a force, but as a geometric feature of spacing. According to this theory, massive objects like stars and planets don't simply sit in space. They bend it. They create dips and curves in the fabric of spacing itself. And other objects follow these curves. That's what gravity is. Not a pull, but a path. Imagine placing a heavy bowling ball on a trampoline. It sinks into the fabric, creating a well. Now roll a marble across the surface. The marble curves around the depression, not because the bowling ball is pulling on it directly, but because the surface itself is curved. That's an analogy, of course, but a useful one. In Einstein's universe, space and time are fused into a four-dimensional fabric, and massive objects reshape that fabric wherever they go. This means that even empty space, the vacuum, the nothingness, is not just a passive stage. It's an active participant. If space can curve, then it can stretch, ripple, and twist. In other words, it has geometry even when there's nothing in it. We see the consequences of this in many surprising ways. One of the most elegant is the bending of light. If light travels through curved space, it too will follow a curved path. We can observe this when light from distant galaxies passes near a massive object like a cluster of galaxies or a black hole. The light bends around the object and reaches us from multiple angles. This effect, known as gravitational lensing, is like watching distant galaxies through a giant cosmic magnifying glass. And it proves beyond any philosophical doubt that space itself has structure. Another curious thing about curved space is that it changes how we understand distance and time. In a curved universe, the shortest path between 2 points isn't always a straight line. At least not as we draw it on paper. Instead, it's a geotic. The natural path that follows the curvature of space. If you've ever flown on an airplane and noticed that your flight path curves northward before descending again, you've experienced this in 2 dimensions. It looks longer on the map, but it's actually the shortest path across the curved surface of the Earth. Now, imagine doing that in 3 dimensions, or more accurately in 4 if we include time. The geometry of nothing affects how we move, how we fall, even how we age. Clocks tick differently in curved regions of spacing. This is not science fiction. It's something we've tested with satellites and atomic clocks. GPS systems, for example, have to account for the effects of both velocity and gravity on time. Without corrections from Einstein's equations, your phone's location would be off by several km every day. Even more remarkable is that this flexible geometry isn't just shaped by stars and planets. It can exist even in deep empty space, regions far from any matter. The shape of that emptiness is determined by the overall structure of the universe itself. Scientists talk about spatial curvature as a large-scale property. Is the universe flat, curved like a sphere, or saddle-shaped? This isn't just a mathematical curiosity. It affects how the universe expands, how galaxies cluster, and what fate awaits the cosmos in the distant future. But wait, how do we even know what the shape of empty space is? After all, we can't exactly float above the universe and take a photo of it. Instead, scientists look at light. Lots and lots of light. In particular, the light from the cosmic microwave background, the oldest light in the universe, which has been traveling through space for nearly 14 billion years. By studying tiny fluctuations in this light, researchers can measure how it has stretched and bent across billions of light years. These measurements tell us that on the largest scales we can observe, the universe appears to be very nearly flat, but not perfectly. So, of course, there's a catch. We can only see so far. Our view is limited by the speed of light in the age of the universe. Beyond that horizon could be more of the same or something entirely different. The shape of space may shift beyond what we can ever measure. It may be flat here and curved there. It may loop, twist, or ripple in higher dimensions. We simply don't know. And that's part of what makes the geometry of nothing so captivating. It challenges our instincts. We like to think of empty space as absence, as the void, the silence between stars. But in reality, space is active. It has properties. It can bend, flex, and even vibrate with gravitational waves, which are ripples in spacing that travel at the speed of light. We detected these for the first time in 2015 when two black holes collided over 1 billion light-years away and sent tremors through the cosmos, gently wiggling our detectors on Earth. Space itself shook. That's the geometry of nothing at work. It may seem like an odd phrase, but the more we study it, the more we realize there's no such thing as truly empty space. Even nothing has shape. Even nothing has rules. And in the vast quiet universe, that shapeless-looking nothing turns out to be one of the most structured things of all. Let's begin with a quiet thought. Imagine you're floating in deep space, far from any planet or star. No up, no down, no wind, no sound. Just you, the silence, and the stars. Now imagine you drop a marble from your hand. What does it do? If you're far from any gravitational pull, it just floats there. But if you're near Earth, that marble will drift gently downward. Not because something invisible is tugging on it with ghostly fingers, but because the very space around Earth is shaped in such a way that the marble naturally moves in that direction. This is the heart of one of the most beautiful ideas in physics. Gravity is not a force. It's a curve. This was Einstein's great revelation. Before him, we had Isaac Newton, who gave us a very successful recipe for how gravity works. According to Newton, gravity was a force that any object with mass exerts on any other object with mass. The more massive the object, and the closer it is, the stronger the pull. It worked perfectly well for apples falling from trees, for cannonballs, and for the orbits of planets. But Newton didn't explain what gravity was, just how it behaved. He even admitted as much, saying he didn't find hypotheses about its true nature. Then in the early 20th century, along came Albert Einstein, hair askew and equations swirling. He dared to ask, what is gravity really? And he found his answer not in force, but in geometry. In Einstein's universe, space and time are not separate things. They're fused together into a single entity called spaceme. This fabric isn't passive. It's dynamic. It bends, stretches, and ripples. And most importantly, it's shaped by energy and mass. Anything with mass deforms the fabric around it. Think of spaceme as a stretchy, invisible mattress. Place a bowling ball in the center and the surface sags. Now roll a marble across the mattress. It curves around the dip, not because the ball reached out and grabbed it, but because the marble is simply following the contours of the surface. That's how planets orbit stars, how moons orbit planets, and how your feet stay planted on Earth. Einstein's theory of general relativity, published in 1915, redefined gravity as the warping of spaceme by mass and energy. His equations are complex, but their consequences are elegant. Instead of a force pulling objects together, objects move along the curved paths created by spaceme itself. Even light, which has no mass, follows these curves. One of the earliest and most striking confirmations of Einstein's theory came during a solar eclipse in 1919. British astronomer Arthur Eddington led an expedition to measure the position of stars near the Sun's edge during the eclipse. The idea was that if Einstein was right, the Sun's mass would bend the light from those stars, making them appear slightly out of place. And that's exactly what happened. The starlight bent, not by a lot, but by just the right amount predicted by Einstein's equations. It was front-page news. Overnight, Einstein became a global celebrity, and the universe quietly reshaped itself in the public imagination. This bending of light by gravity isn't just a neat party trick. It's something we see in space all the time. Massive objects like galaxies or clusters of galaxies can act as gravitational lenses, bending and magnifying the light from even more distant galaxies behind them. These lenses allow us to peer deeper into space than we ever could otherwise. Seeing galaxies from the early universe that would otherwise be too faint to detect. It's cosmic optics on the grandest scale. But general relativity doesn't stop at bending light. It also tells us that time itself is affected by gravity. Clocks run slower in stronger gravitational fields. This is called gravitational time dilation. And though it sounds like science fiction, we've measured it. Place two ultra-precise atomic clocks at different altitudes, say one on a mountain and one at sea level, and over time they'll fall out of sync. The one closer to Earth's center, where gravity is stronger, ticks ever so slightly slower. If you've ever used GPS, you've benefited from this insight. The satellites that make GPS possible orbit high above Earth, where gravity is weaker and time runs just a bit faster than it does down here. If engineers didn't account for both gravitational time dilation and the effects of special relativity, which deals with the speed of the satellites, your phone's location could be off by several kilometers. Einstein may not have had Google Maps in mind when he developed general relativity, but without him, it wouldn't work. Perhaps one of the most dramatic predictions of general relativity is the existence of black holes. Regions of space where the warping of spacing becomes so extreme that nothing, not even light, can escape. Black holes were once thought to be mathematical curiosities, but now we know they're real and they are out there lurking in the centers of galaxies and spinning invisibly through space. In 2019, we even captured an image of one, a blurry, glowing ring surrounding a shadowy void. It was like seeing Einstein's equations come to life. More recently, in 2015, scientists announced the first detection of gravitational waves, ripples in the fabric of spacetime caused by massive objects like black holes colliding. These waves stretch and squeeze space itself as they pass by, and detecting them required instruments so sensitive they could measure distortion smaller than a proton. The very idea that space could ripple like water still feels astonishing. But we've now detected many such events, each one a kind of cosmic chime from the universe's most extreme cataclysms. All of this, the bending of light, the slowing of time, the orbiting of planets, the existence of black holes and gravitational waves, comes from a single idea that mass and energy tell spacetime how to curve and curved spacetime tells objects how to move. It's a neat little loop and it works with stunning precision. And yet, despite its successes, general relativity isn't the whole story. At very small scales inside atoms, for instance, it doesn't mesh well with quantum mechanics, our other great theory of nature. Trying to unify these two frameworks remains one of the biggest puzzles in modern physics. But that doesn't diminish what general relativity has achieved. It remains one of the most beautiful and successful scientific theories ever devised. There's something deeply poetic about it, too. The idea that gravity is not a tug but a tilt, that the universe is shaped not by strings and pulleys but by elegant curves and invisible waves is both humbling and awe-inspiring. We live our entire lives under the influence of these curves. We sleep, wake, walk, and dream while space-time gently cradles us in its invisible hands. And most of the time we don't even notice. Gravity, for all its might, is silent. It has no color, no taste, no smell. It doesn't hum or buzz, but it shapes everything. From the arc of a thrown stone to the motion of galaxies, it is the quiet geometry behind all movement. Einstein gave us the tools to see that, to understand the world, not just as a collection of forces, but as a graceful curving dance of space and time. And in that vision, even nothing becomes something. Even silence has structure. And the invisible becomes the architecture of reality itself. When most people hear the word flat, they probably think of a pancake, a piece of paper, or that one tire that always lets you down when you're running late. But in cosmology, flat has a much more fascinating meaning. One that could reveal the very architecture of the universe. The question of whether space is flat, curved inward like a sphere, or curved outward like a saddle is one of the most profound in physics. It shapes how we think about everything from the Big Bang to the fate of the cosmos. Let's begin with the basics. Imagine a triangle on a flat surface like a sheet of paper. If you draw a triangle and measure the angles, they'll always add up to 180 degrees. That's a hallmark of flat or Euclidean geometry. Now imagine doing the same on the surface of a sphere like a globe. You can draw a triangle with 390 degrees angles. Say from the equator to the North Pole and back again. And suddenly the sum is 270 degrees. That's not flat geometry anymore. That's positive curvature. On the flip side, imagine a saddle shape. If you draw a triangle there, the angles will add up to less than 180 degrees. That's negative curvature. Now, take these simple ideas and scale them up, way, way up. Instead of measuring triangles on paper or globes, imagine drawing them between galaxies using beams of light as your lines. That's essentially what cosmologists do. By examining the paths light takes over billions of light years and how distant objects appear to us, we can infer whether space is flat, curved inward, or curved outward. But what do we actually mean by these three shapes? In a cosmic sense, a flat universe means that parallel lines stay parallel forever. It also means the rules of Euclidean geometry hold up even at cosmic distances. Triangles still add up to 180 degrees. And light travels in straight lines that aren't warped by the curvature of space, except of course when it passes near massive objects like stars or black holes, which create local distortions. On the whole though, flat space is the vanilla flavor of the cosmos. Simple, infinite, and perfectly balanced. A closed universe, on the other hand, has positive curvature. It's like the surface of a sphere, but in 3 dimensions. In this model, if you travel far enough in one direction, you could hypothetically end up back where you started without ever turning around. It's a finite universe, but one with no edges. There's no outer wall to bump into, no void beyond the boundary, just a loop closed upon itself. This type of universe could eventually stop expanding and start contracting, leading to a big crunch scenario, a reversal of the Big Bang. Then there's the open universe, which has negative curvature. Picture an infinite saddle that stretches in all directions. It never loops, never closes, and just keeps going forever. This model suggests a universe that will expand forever, growing colder and emptier over time. Galaxies will drift apart. Stars will burn out. And in the far future, even atoms may decay into silence. Each of these shapes isn't just a matter of geometry. They have profound implications for how the universe behaves and what its future might look like. But here's the tricky part. How do you measure something as enormous as the shape of the entire universe? You can't exactly fly out to the cosmic edge with a measuring tape and check where the space bends. Fortunately, the universe has left us some clues, and one of the biggest is light. In particular, the light from the cosmic microwave background, the afterglow of the Big Bang, offers a snapshot of the universe when it was only about 380,000 years old. This light has been traveling through space ever since, stretching and shifting as the universe expands. When we observe this ancient radiation, we see patterns, tiny fluctuations in temperature and density that tell us how matter was distributed in the early cosmos. By measuring the angular size of these fluctuations, scientists can determine whether space is flat or curved. If the universe is flat, those patterns appear at a certain expected size. If space is positively curved, the light paths converge and the fluctuations look larger. If it's negatively curved, the light paths diverge and the fluctuations look smaller. It's a bit like looking at a chessboard through different lenses. Curved ones stretch or shrink the pattern, while a flat lens keeps it unchanged. These measurements are incredibly precise. Thanks to data from satellites like COBE, WMAP, and the more recent Planck mission, we know that the universe appears to be very nearly flat. But here's the catch. It's only flat within our observable horizon. Beyond that, we simply don't know. The universe could still curve at scales larger than we can see. It could loop, ripple, or twist in ways forever beyond our detection. Our cosmic map is vast, but it still has edges. What's even more remarkable is that this flatness isn't just some cosmic coincidence. In fact, the early universe had to be astonishingly well balanced for space to appear so flat today. If the universe had even a tiny bit too much energy density, it would have quickly curved inward and collapsed. Too little, and it would have flown apart too quickly for stars and galaxies to form. This precise balance is known as the flatness problem, and it puzzled physicists for years. One elegant solution is the theory of cosmic inflation. This idea suggests that in the first tiny fraction of a second after the Big Bang, the universe expanded faster than the speed of light, not violating relativity because space itself was expanding. This rapid inflation smoothed out any wrinkles or curves, flattening the universe like steam pressing a shirt. It's like blowing up a balloon so large that any tiny curve on the surface becomes invisible to someone standing on it. Inflation not only explains the flatness of space, but also the uniformity we see across the cosmos, even in regions that seem too far apart to have ever communicated. Still, even with these insights, the shape of the universe remains one of the biggest mysteries in cosmology. Is it perfectly flat, just nearly flat? Is there a subtle curve we haven't yet detected? Or could space have a strange topology, looped or folded in ways that mimic flatness at smaller scales? And what about edges? People often wonder whether the universe has a boundary. But in curved geometry, boundaries aren't always necessary. A two-dimensional creature living on the surface of a sphere wouldn't encounter an edge. They would just keep walking and eventually circle back. Likewise, a closed universe has no edge, but is still finite. Meanwhile, a flat or open universe could be infinite with no center, no boundary, and no place you could call the end. This all makes flatness sound deceptively simple. But flat space is still a vast and mysterious thing. It could stretch forever. It could hide strange topological twists. It could even be part of a multiverse, one of many patches of spacing with different curvatures or dimensions. In the end, asking whether space is flat is like asking what kind of canvas the universe is painted on. And the answer, as far as we can tell, is a nearly flat one stretching into darkness, whispering subtle clues about its shape in the light of ancient stars. Whether it loops, curves, or stretches beyond imagination, space holds its shape in silence, waiting patiently for us to measure its angles and ask again what it all means. Let's take a deep breath and imagine just for a moment that everything around you is getting farther away. Not in a panicked, "Where did I leave my wallet" sort of way, but calmly, steadily, silently. The chair beneath you, the stars above, the space between galaxies, it's all stretching. Not because things are flying apart through space, but because space itself is expanding. This isn't science fiction. It's one of the most extraordinary facts about our universe. The cosmic stage we're standing on is growing. But what does that really mean, and how do we know it? The story begins nearly 14 billion years ago with the Big Bang. Contrary to how it's often portrayed, the Big Bang wasn't an explosion in space. It was the rapid expansion of space itself. There was no outside for it to explode into and no center where the bang occurred. Instead, every point in the universe began expanding away from every other point. Like a loaf of raisin bread rising in the oven, the raisins standing in for galaxies move apart not because they're propelling themselves outward, but because the dough around them is stretching. This idea was first hinted at in the early 20th century when astronomer Edwin Hubble observed that distant galaxies were moving away from us. Not only that, but the farther away they were, the faster they seemed to be receding. This discovery, now known as Hubble's law, was a game-changer. It meant the universe was not static, as many had believed, but dynamic. Something was causing the vast distances between galaxies to grow. So, what was going on? It turns out that the very fabric of space can stretch. Space is not a static backdrop like a cosmic wallpaper. It's a flexible evolving structure. And general relativity. Einstein's revolutionary theory allows for such stretching. His equations describe how the geometry of space and time evolves over time in the presence of energy and matter. When applied to the universe as a whole, they predict a changing cosmos, either expanding or contracting. The expanding model quickly became the front runner, especially once cosmic microwave background radiation was discovered in the 1960s. This ancient light left over from the early universe is a faint glow that fills all of space. It's a bit like the thermal aftershocks of the Big Bang. A gentle cosmic hum in the background. The fact that this light is still around and that it has been stretched into longer and cooler wavelengths over time is compelling evidence that the universe has been expanding for billions of years. A popular analogy to explain this is the balloon metaphor. Picture the universe as the surface of a balloon. Now draw a few tiny dots on it to represent galaxies. As the balloon inflates, the dots move farther apart. Not because the dots themselves are moving, but because the surface they sit on is stretching. The key is that every dot sees every other dot moving away. There is no special center, no edge, just expansion happening equally everywhere. This analogy helps explain a few tricky ideas at once. First, there's no edge to the universe, at least not in any conventional sense. The surface of a balloon doesn't have an edge for a two-dimensional creature living on it. It's finite but unbounded. Second, no matter where you are in the universe, it looks like you're at the center of expansion. That's not because you're special, but because everything is moving apart in all directions. Now, here's a question people often ask. If the universe is expanding, why aren't we? Shouldn't your body, your house, and your sandwich be stretching, too? Happily, no. You're safe from cosmic inflation, at least at the personal scale. That's because expansion only dominates on very large scales where the pull of gravity, electromagnetism, and nuclear forces are too weak to resist. Your atoms, molecules, and muscles are all tightly bound by forces much stronger than the gentle stretching of space. The Earth isn't expanding. The solar system isn't expanding. Even our galaxy isn't expanding. The universe's growth only becomes noticeable when you zoom out far enough. Hundreds of millions of light years where galaxies themselves are not gravitationally bound to one another. Think of it this way. If the universe were a giant sponge slowly swelling in water, your body is like a chunk of iron embedded in the sponge. Local structures resist the stretch, but the sponge as a whole still grows. Another question that tickles the brain. What is the universe expanding into? This is where the balloon metaphor can be a bit misleading. While the surface of a balloon expands into the air around it, our universe isn't expanding into anything. Space itself is growing. There's no external space. It's spilling into, just more space being created between things. From a mathematical point of view, the coordinates describing the universe are stretching. It's not that galaxies are flying through space like shrapnel from an explosion. They're staying where they are while space swells around them. This expansion also affects how we see distant galaxies. Light traveling through expanding space gets redshifted. Its wavelength stretches out, making it appear redder and less energetic. The more distant a galaxy is, the more its light has been redshifted by the time it reaches us. In fact, some galaxies are so far away that the space between us and them is expanding faster than the speed of light. That doesn't violate any laws of physics because it's space itself expanding, not objects moving through space. This means there are regions of the universe we will never see. Their light will never reach us no matter how long we wait because the space between us is stretching too fast. These unreachable areas form what's called the cosmic event horizon. A kind of ultimate limit on what's observable. It's a humbling thought. Not only is the universe expanding, but parts of it are vanishing beyond our view forever. And yet, in the grand of the cosmos, this expansion tells us something profound. The geometry of the universe, the way space curves, the way time unfolds, is not frozen in place. It evolves. It stretches. It carries the past forward, one expanding moment at a time. And we're all passengers on this gently growing stage. One of the most mind-bending discoveries in recent decades is that this expansion is actually accelerating. In the late 1990s, astronomers observing distant supernova noticed that these exploding stars were fainter than expected. Not because they were farther away due to normal expansion, but because the universe had been speeding up. Something was pushing galaxies apart faster and faster over time. This mysterious driver of expansion has been dubbed dark energy, and it currently makes up about 70% of the total energy content of the universe. We don't know exactly what it is. It doesn't clump. It doesn't emit light, and it seems to act like a constant pressure woven into the fabric of spacing. Whatever it is, it's making the universe balloon more rapidly with each passing moment. As the expansion continues, distant galaxies will eventually slip out of sight. In tens of billions of years, observers in our galaxy, if any, remain, might see only the faint glow of nearby stars, unaware that the universe ever had billions of others. The sky could go dark, not from nightfall, but from cosmic solitude. But for now, we are fortunate. We live in a time when we can still see the echoes of the Big Bang, still trace the patterns of galaxies, and still measure the stretch marks of space itself. The universe is expanding, and with each measurement, we're learning to read its shape. Written not in stone, but in the stars. Imagine a universe as flat as a pancake. Though, in this case, there's no syrup, no plate, and definitely no edge to fall off. Just an endless smooth expanse stretching in every direction, quietly going about its cosmic business. That's the idea behind a zero-curvature universe. A cosmos so geometrically well-behaved that it might make even Euclid nod in approval. In this kind of universe, the rules of geometry behave just as we expect them to from our middle school math class. Triangles always have angles that add up to 180 degrees. Parallel lines, if perfectly drawn, never intersect, not even after crossing billions of light years. Circles have the same relationship between diameter and circumference, no matter where you draw them. And a straight line really is the shortest distance between 2 points. It's the gold standard of flatness. No bulges, no warps, no satellite dips, just clean, crisp, infinite space. But what does it mean for an entire universe to be flat? First, it's worth clearing up a small misconception. When cosmologists say flat, they don't mean two-dimensional like a sheet of paper. A flat universe is still three-dimensional. Length, width, and height. What makes it flat is its curvature, or more specifically, its lack of curvature. Imagine walking across a room in a straight line. In a flat universe, you can keep walking forever without curving back toward where you started or drifting subtly away from your original path due to warp geometry. Your path remains straight forever. It's space behaving like an infinite floor, not like the surface of a sphere or a saddle. So, how does scientists determine whether the universe is actually flat? After all, we can't exactly stretch a cosmic ruler from one galaxy to another and check for bends. Instead, we look at how light travels across the universe, specifically how it stretches and spreads over billions of years. One of the most powerful tools we have for this is the cosmic microwave background, the faint afterglow of the Big Bang. This ancient light has been traveling through space for nearly 14 billion years, carrying with it clues about the shape of everything it's passed through. By analyzing the size and distribution of tiny temperature fluctuations in this light, scientists can test whether space is curved. Here's how it works. If the universe is flat, light from these distant fluctuations travels in straight lines and the patterns appear at predictable sizes. If space is positively curved, like a sphere, the light converges a bit, making the patterns appear larger. If space is negatively curved like a saddle, the light diverges and the patterns appear smaller. Thanks to data from missions like WMAP and Planck, we've measured these patterns with extraordinary precision. And the result, the universe appears to be very nearly flat. But nearly flat is not the same as perfectly flat. The universe could be incredibly close to zero curvature without quite getting there. Like a pancake so vast that any slight curve is imperceptible even across billions of light years. Or perhaps it's exactly flat down to the finest decimal in a kind of cosmic balancing act that stretches from one end of time to the other. If it is perfectly flat, it implies something extraordinary. A flat universe doesn't just mean tidy geometry. It also hints at a very specific amount of energy and mass. In cosmology, this is called the critical density. The precise balance point between too much matter, which would cause the universe to eventually collapse, and too little, which would allow it to expand forever. A flat universe sits delicately between these two extremes. It expands forever, but more and more slowly, approaching a kind of cosmic cruising speed. Interestingly, when scientists first calculated the amount of matter and energy in the universe, they found only about 5% of what was needed for flatness. That included everything we could see. Stars, gas, dust, planets, even black holes, not nearly enough. But then came dark matter, an invisible form of matter detected only through its gravitational pull. That added another 27% or so to the tally. Still short, the rest. It turns out the remaining 68% appears to be made of something even stranger. Dark energy, a mysterious pressure woven into the fabric of space itself, pushing galaxies apart and accelerating expansion. Put all of that together, ordinary matter, dark matter, and dark energy, and the total density of the universe seems to land almost exactly at the critical value for flatness. It's a bit like throwing a dart blindfolded and hitting the bullseye from 1,000 miles away. This uncanny balance is one of the great puzzles in cosmology. Why should the universe be so precisely flat? Coincidence? Design? A deeper law of physics we haven't yet discovered. One possible explanation is cosmic inflation, a theory that suggests the universe underwent a brief but incredibly rapid expansion in its earliest moments. During this split second, any initial curvature would have been smoothed out, just like blowing up a balloon until any tiny bumps or dents disappear. Inflation is a bit like a cosmic iron flattening spaceme into a near-perfect sheet. If this theory is right, it could explain why the universe looks so flat today, even if it didn't start that way. But let's reverse it. Over time, the universe could stop stretching and begin to contract, leading to a possible scenario known as the Big Crunch, where everything collapses back into a hot, dense point, perhaps to start the cycle again. Whether or not the universe will actually end this way is still an open question, but the closed model makes it possible, and it paints a poetic picture. A universe born in fire, expanding for billions of years, then cooling, pausing, and finally collapsing back into silence. What's fascinating is that you wouldn't necessarily feel any of this curvature in your everyday life. You don't float slightly uphill in one direction or notice objects behaving oddly when you walk through your living room. On small scales, say inside galaxies or solar systems, the curvature is negligible. It's only when you start connecting points across hundreds of millions or even billions of light years that the shape becomes apparent. So, how do cosmologists look for clues? One method involves studying the cosmic microwave background, the ancient light left over from the Big Bang. This light acts like a snapshot of the early universe, frozen in time just 380,000 years after its birth. Scientists analyze the angular size of tiny temperature fluctuations in this background radiation. If the universe is closed, these fluctuations appear slightly larger than they would in a flat universe because light paths converge as they move through curved space. Another method involves the distribution of galaxies on the larger scales. In a closed universe, the way galaxies are clustered and how their light is redshifted, stretched by the expansion of space, can give hints about the geometry. If we observe patterns that suggest convergence, just like those triangle angles growing too large, it could be a sign that we're inside a curved cosmos. The most recent measurements, particularly from the Planck satellite, suggest that the universe is very close to flat, but there's still a little wiggle room for positive curvature. Some analyses even hint ever so slightly at a closed universe. But the margin is tiny, and the uncertainties are real. It's like trying to tell whether the Earth is perfectly round by standing in your backyard and squinting at the horizon. You need very precise tools, and even then, you're still stuck with only a limited view. There's another curious thing about closed universes. They can support multiple paths between 2 points. That means you could, in theory, shine a flashlight in one direction, and if you waited long enough, the light could loop around the universe and hit you from behind, like mailing a postcard to yourself by tossing it into orbit. Of course, the actual travel time would be measured in billions of years, so it's not exactly a practical method of communication, but it's a delightful thought. This looping nature also opens up questions about the topology of the universe, its global structure. Could space be shaped like a three-sphere, a three-dimensional analog of the surface of a regular sphere? Or might it be something even more exotic like a pancare-dodecahedral space where space loops in intricate repeating patterns? These ideas are not just theoretical toys. Some cosmologists believe subtle patterns in the cosmic microwave background might hint at such hidden topologies, though the evidence remains elusive. If we really do live in a closed universe, it might offer some comfort. In an infinite universe, you can always wonder if something lies beyond. But in a closed one, there is no beyond. Every direction eventually brings you back. It's a complete cosmos, self-contained and elegantly curved. A place where the story of everything is written not on a boundless scroll, but on a cosmic sphere. It might sound a little claustrophobic, this idea of a finite universe, but it's not. There's still room for an unimaginable number of stars, galaxies, and wonders. Finite doesn't mean small. It just means that the cosmos wraps around itself, gently bending the rules of geometry into a loop. And even if we never prove beyond all doubt that our universe is closed, the possibility offers a beautiful reminder that space isn't just a void. It has shape. It has character. And it might just be gently curving beneath our feet, whispering across billions of light years that all paths eventually circle home. Let's go somewhere vast. Not just big or really big, but endlessly big, and then some. Picture a universe that stretches in every direction, never loops, never curves back, and never even thinks about calling it a day. A universe that expands not into something, but into itself forever. That's the unsettling yet oddly beautiful vision offered by the open universe. A cosmos shaped not like a balloon or a pancake, but like a saddle that never ends. This is a universe with negative curvature. That might sound a bit gloomy, but in geometric terms, it simply means the rules of space are bent in the opposite direction of a sphere. Instead of curving inward like the surface of a globe, space curves outward like the seat of an old wooden saddle, dipping down in one direction and arching up in another. It's called hyperbolic geometry, and it changes the way space behaves in quiet but powerful ways. Let's start with the basics. In an open universe, triangles act a little strangely. If you draw a triangle with 3 straight lines, what mathematicians call geodesics, the angles will add up to less than 180 degrees. The bigger the triangle, the greater the discrepancy. Parallel lines don't stay the same distance apart. They diverge over time. And if you were to draw a circle and measure its circumference, you'd find it was larger than expected based on its radius. In short, everything stretches out just a little more than your intuition says it should. But what does that mean on a cosmic scale? In the open universe model, space doesn't wrap around itself. There are no closed loops, no secrets, no paths that eventually bring you home. Instead, space extends infinitely in every direction. You could travel in a straight line for eternity and never cross your own path. Not because you're going in circles, but because there's simply too much room to ever run out of it. This type of geometry arises when the total energy density of the universe is less than a specific critical value. That includes all the matter, radiation, dark matter, and dark energy added together. If the density is too low to slow down cosmic expansion in a meaningful way, the universe ends up with negative curvature. There's not enough gravity to ever bring the expansion to a halt, let alone reverse it. Instead, the universe expands forever, cooling, dimming, and becoming ever more diffuse. It's a quiet, haunting picture. Over billions and trillions of years, galaxies drift farther and farther apart. The stars exhaust their fuel and fade to black. The matter left behind, cold husks of stars, drifting planets, and the occasional stubborn black hole spreads thinner and thinner. Eventually, the night sky might go completely dark. Not because anything exploded or ended, but because everything simply drifted out of view. That's the ultimate fate of an open universe. A slow, graceful fade into the void. But how would we know if we live in such a place? Once again, cosmologists turn to the ancient light of the cosmic microwave background, the leftover glow from the Big Bang. By studying how this light spreads and how its tiny temperature fluctuations appear across the sky, scientists can infer the geometry of space. In an open universe, these fluctuations appear smaller than expected. The light has traveled along diverging paths, spreading out more than it would in flat or positively curved space. Observations from satellites like WMAP and Planck suggest that the universe is very nearly flat with only a tiny margin for error. That means the open model, while still a contender, is not the current favorite. But it's far from ruled out. There's still a chance, however slim, that our universe does in fact have a touch of negative curvature. The saddle shape might be subtle, stretched across such an enormous scale that we only notice it in the most delicate measurements. And then there's the matter of topology. Even an open universe could have a complex twisted global structure. While negative curvature means infinite extent in the traditional model, some variations could involve strange shapes, multi-connected wraparound structures that mimic infinity in clever ways. Think of space as a video game map that repeats, but not quite like you'd expect. These ideas are speculative, but they add a layer of delightful weirdness to an already strange concept. One thing that sets an open universe apart is its relentless expansion. In this model, the universe doesn't just drift apart, it accelerates into emptiness. And once that expansion gets going, it doesn't stop. Galaxies recede from one another at ever-increasing speeds. Eventually, they become so far apart that light from one can no longer reach the other. Communication becomes impossible. Observation becomes impossible. Each galaxy becomes an isolated island alone in a sea of expanding darkness. Now, that might sound a bit bleak, but there's another way to look at it. An open universe is limitless. It offers infinite potential for discovery, for exploration, and for thought. Every direction is a path you haven't taken. Every patch of sky is a doorway to the unknown. In a saddle-shaped cosmos, the universe doesn't cradle you gently in a curved loop. It challenges you to step into the infinite, to keep moving forward without end. And there's something comforting in the consistency of it. No hidden loops, no unexpected returns, just straight lines, diverging paths, and a clean, honest geometry. It's the universe as an open road, not a maze. Some might find that lonely. Others might find it exhilarating. Interestingly, negative curvature also plays a role in mathematics and art. Hyperbolic space has fascinated artists like Max Scher, who used it to create intricate repeating patterns that shrink toward infinity. In nature, hyperbolic shapes appear in coral, lettuce, and the delicate lacework of sea slugs. Even in our everyday world, the geometry of the saddle shows up in places you wouldn't expect, like Pringles, which, yes, are technically hyperbolic paraboids. Back in the cosmos, the open universe also has implications for time. In this model, time stretches endlessly forward, never cycling back. There's no big crunch waiting at the end of the line. Just more time, more space, and more questions. Physicists describe this as a cold death or heat death scenario where entropy reaches its maximum and the universe becomes a calm uniform void. It's not a dramatic ending, more like the universe slowly falling asleep. Even if our universe isn't open, the very idea of it expands our imagination. It reminds us that space isn't necessarily bound or curved in friendly ways. It can be wild, vast, and uncaring of our need for closure. It can stretch beyond what we can see or even imagine, and it may never stop stretching. The open universe is like a story with no final chapter, just pages drifting into the unknown. It's infinite in scope, rich with mathematical mystery, and quietly humbling. In a cosmos shaped like a saddle, the journey is never over. And for all its emptiness, it offers something truly profound. The freedom of forever written into the very shape of space. If you could hold a telescope so powerful it peered into the deepest past, you'd eventually see something astonishing. Not the edge of the universe, but its beginning, or at least a kind of cosmic fossil record of it, a faint ancient glow. Not bright like starlight, but cold and gentle. It's been traveling through space for over 13.8 billion years, and it's still here, softly bathing the universe. This is the cosmic microwave background, or CMBB for short. And it's one of the most important clues we have about the shape and story of everything. Imagine a photograph not of your family or your dog wearing sunglasses, but of the entire universe as a baby. The CMBB is just that, a portrait of the cosmos when it was only about 380,000 years old, which on a cosmic timeline is practically its newborn stage. It's a snapshot of a moment when the universe transitioned from a hot, dense, opaque fog into something transparent and open. Before this point, the universe was filled with a searing plasma of particles and photons constantly colliding. Light couldn't get very far without being scattered like headlights in a thick fog. But then something miraculous happened. The universe cooled down enough for protons and electrons to combine into neutral atoms. This process, called recombination, allowed light to finally move freely. Those newly liberated photons have been traveling through space ever since, stretching out into microwave wavelengths as the universe expanded. And today, we can detect that ancient glow with specially tuned instruments. Now, if you could see the CMB with your eyes, the entire sky would glow faintly in all directions. It's not a bright glow. It's just a few degrees above absolute zero. But it's everywhere and it's astonishingly uniform. In fact, for a long time, that uniformity was a bit of a puzzle. The CMB is smooth to within a few parts in 100,000. But it's those tiny variations, those tiny temperature wrinkles that hold the secrets to the shape of space itself. These minute fluctuations represent slight differences in density in the early universe. Regions that were just a little bit denser than their surroundings would eventually grow into galaxies, clusters, and cosmic structures. Think of them as the seeds of everything we see today, from spiraling galaxies to sleepy planets. And by mapping these fluctuations across the sky, we can learn an incredible amount about the geometry of the universe. Here's how it works. Imagine drawing a triangle on the sky using the light from 3 distant points in the CMBB. The shape and angles of that triangle will behave differently depending on the curvature of the universe. If space is flat, the angles will add up to 180 degrees just like in normal geometry. If space is positively curved like a sphere, the triangle's angles will add up to more than 180 degrees. And if space is negatively curved like a saddle, they'll add up to less. Now, we can't exactly take out a giant protractor and measure triangle angles across the cosmos, but we can do something similar. Scientists study the angular size of temperature fluctuations in the CMB. There's a characteristic size about 1 degree across that corresponds to the distance sound waves could have traveled in the early universe before recombination. This scale is like a standard ruler imprinted on the sky. If the universe is flat, we see this ruler at its actual size. If the universe is curved,